Morning. So I think we can go ahead and begin. So before we get into the variational principle, I just want to mention the the homework assignment problem. So I've been asked by already two people already that I don't think that they will be able to finish the assignment by tomorrow. So I've been asked to extend that. So I was thinking it will depend, the extension will depend on how far people are. So I know one student that has not started the tutorial, but I think the rest of you by now, let's see. I'm thinking maybe by Wednesday. So my suggestion is Wednesday due date then. But it depends on how far you were with the original homework assignment. So is everyone happy with if we move it to well, one. I think then because there are no objections, then the new will be Wednesday, submitted before by midnight. And then the next thing that I was asked was some people are really having a difficult time with the so I've been asked to give you further hints. So I'll start with the problem that the hint for the harmonic oscillator type of problems, which I think I had already done something similar in the lectures, but I'll just revise that because maybe it might be that I went through those types of problems very quickly. So I think it's question 4, the one with the, okay, there are there are two of them, but the one with the isotropic harmonic oscillator. So if you write that, and another thing that I realized, I think one of you pointed it out, it's just that there's a typo in the hint in terms of how you are supposed to write the creation operators for AX and AY. That my point was that just try to use creation and annihilation operator to do those types of, to use the Hermite polynomials. So if you look at the, so I started with some unperturbed Hamiltonian, which will just be minus h bar squared over 2. It's, maybe I should write that as delta squared plus half omega squared x squared plus y squared plus z squared. Now this problem you cold solve exactly, and the eigenfunctions which differ from those of the lecture, I'm saying that they are going to be labeled by some integer n, and they're going to be a direct product. So they're going to be some integer depending on x direction, one depending on the y direction, and one depending on the nz direction. In the I just left it as that notation. You could also, or to keep track of what I'm doing, you could label them as nx, ny, and nz. Right. Now, if you look at the energy, so E, this will be given by it's h bar omega, it's x plus the half for the x direction, plus ny plus the half, plus nz plus the half. So this means that the energy for this end state will be given by h bar omega nx plus ny plus nz plus 3 over 2. Right. So then you look at the ground state. Right. So the ground state will be the state that, so the first state will just have an energy 3 h bar omega. right? Or 3/2. This corresponds to the state having 0, 0, 0. So this is the ground state and it's not degenerate. So here you can go and use first order and second order perturbation theory to calculate the corrections of any thing that I add. However, the first state, so there will be the first state which will have energy, I think it's 5/2 h bar omega. This 5/2 you get either by setting this to be 1, to be 0, 0, right? And or you have 0, 1, 0, you have 0, and 1. So this state is already threefold degenerate. So what I was asking you to do was to then, the first thing for degenerate perturbation is that you have to form 3x3 matrix, right? So you have three states. So I might like that I call the first vector 1 to be 1, 0, 0. Second vector I called 0, 1, 0. Then the third vector I called 0, 0, 1. And you have to form by 3 matrix. So for example, so one of the complaint, or not a complaint, difficulty was that the three-dimensional one seemed to be much more difficult. Let me just put, so I started with that unperturbed Hamiltonian. These were the energy states, right? And they were degenerate. For example, the first energy state was degenerate. Then what I did was that now I've added a similar perturbation, which was xy. And I'm asking what are the energy corrections. So what you do, so here there will be things like H31, H32, and H33, and similarly. Right? And now if you look at the perturbed Hamiltonian, there is no Z dependence. That is why I would suggest that you start by computing these things, because what's going to happen if you check, let's say that you have these ones with the 3, so the 3 has 0, 0, 1, so this would be 0 vector 0 and another vector 1, and it's acting on xy, right? And you have 1, let's take maybe h1, which is that vector there. So you get 1, 0, 0. Right. Now the perturbed Hamiltonian, it's not depending on z, so it doesn't touch this. It doesn't touch that part there, and it also doesn't touch that part there. So you end up with something like 0, 0, which is shortened for these two type of vectors. You still have an x and y, and they're still acting on 1, 0 part. But these vectors, maybe I should not have used that x marks the spot, or this 1 there and that 0, right? They do not act anywhere on x and y. They just stay by themselves. What is this? Obviously, it's an inner product in Hilbert space. It's a real number or complex number depending on the vector space. Yes. So these eigenstates of the original unperturbed Hamiltonian, they are orthonormal. So whenever you take any one of them, an x and an x prime, maybe I should have used, they're orthonormal. So this is 0. So then this gives you a 0 there. And because they are symmetric, h3 1, it's the same vector. It's just that now you, instead of you having this 0 0 1, now that 0 0 1 it's there, and you've just swapped them around, but the same argument. So here you will end up with something like 0 1 0 1. So this is again 0. The same with 3 2. The point is that if you're looking at the overlap between the third vector and any of them, they will they will give you 0, because um, x y doesn't touch these variables. So you get either 1 with 0, right, or you get 1 with the other 0. So your eigen, your matrix then will look like 0 0 on top 0 0. So the only thing that you'll have to compare is this one, because what happens when you have 3 and 3 is that you have x y there, 0 0, is it 0 0 0, and then you have 0 0 1. And I'm saying for the last maybe 10 minutes that these operators do not act on the third row. So the third row in this is you get 1 with 1, and this is normalized to, you still have to compute what is 0 0 acting on x y 0 0. So your matrix then, it's already starting to look like, is you get 0 0, some number here, 0 0, and this matrix then is everyone happy as to how to compute this other 2 by 2 matrix sitting there? Right. So to repeat, I have something like HP is given by lambda xy. And for example, I'm trying to find what is h11. So h11, my vector I chose to be 1 0 0 x y 1 0 0. Right. So let's see. Depends on x. That also depends on x. So it's just that in the lecture, I tended to write them as out explicitly. So I was writing them in this form. I mean, some people, if they want, it's multi, and this is x, but you end up with a sandwich between 1 x and 1 0 x 0, not 0 1. This is y, and then the z part doesn't touch anything, so you just get 0 with 0, but 0 0 is 1. And what is this? No, that's correct. So they are Gaussian integrals, but the reason is that I want you to avoid using the Gaussian integrals with Hermite polynomials. They're not really, you have E minus alpha x squared, then you start playing around with these Hermite polynomials. This is where that hint comes in, which I wrote incorrectly. So you know that your x is going to be given by square root of h bar over 2m omega in terms of creation and annihilation operators. Right. So again, did this in the lecture. You let it act on n in general. So let's say this is ax, right? A a a plus is a creation operator. So when this acts there, it will give you n plus 1 square root n plus 1. This is annihilation, so it lowers the state by 1. So this gives you n minus 1. Physically, it destroys a particle, so you end up with n minus 1 particles, and the normalization was square root n. Right? And then xn with n. Right? So you're just going to sandwich another n there. So you put an n there, put an n, put an n, put an n. So the final thing will just, and this is, let me write it properly, it's n. So you get n. These wave functions are orthonormalized. So this gives you delta n minus 1 plus square root n plus 1 delta n plus 1. So this could be, as someone answered, this could be Gaussian integrals, maybe with the 43rd Hermite polynomial. You then have to start plugging 43, blah, blah, blah. But if you just use creation and annihilation operators, this is the result that you get. And this is 0. Right? There is no integer that is equal to, it's like the 43 can never, if you will look 43rd eigenstate, 43 will never be equal to 44. And the same thing, 43 will never be equal to 42. So this is automatically 0. So for this exercise, you can use the fact that for n, the diagonal elements of the unperturbed Hamiltonian harmonic oscillator, they're all 0. So this is 0 multiplied by 0 multiplied by 1. So this is 0. And you can check H22, right? H22 will give you, I chose it to be 0, 1, 0, x, y, 0, 1, 0. So you end up with 0, x, 0. Again, this is automatically 0 because of this statement here. So the only non-zero that I can see being non-zero is this element here, and because it's symmetric, once you calculate this one, you know this one, so you only have to calculate something like h1, h12, and also, yeah, once you have that, or if you want, you can also check h21, and the other one would be h33. I think these are the ones that you have to check that are non-zero. And given that I see that people are not that happy with this notation, let's look at what will happen maybe for the next one, right? So in one of the problems, you have to find what is x4 acting on. Basically, you know that the correction will be given by n x4 to the n. In one of your problems, I think I've made the perturbation to just be x4. So then you have to start finding what is this. So you do what I did, you start with x acting on n, write it in terms of creation annihilation operator to m omega a plus a dagger. So I think this gives you, if you look at the previous stuff, n minus 1 plus square root n plus 1 square root n plus, that's a vector n plus 1. Then you hit it again with another x. So this gives you x squared. So x, so you end up with h bar over 2m omega a plus a dagger. And then now it's acting on the result that you got when x was acting on n. Right. So let's only look at this one because of time. H bar over 2 omega square root n. When a adds there, it raises it by 1. So this just gives you n, right? N minus 1 plus 1 will just give you n. And the a dagger acting on some state gives you square root m plus 1, vector m plus 1. So this will give you, we add a 1, but again, we'll have that square root n. And similarly, once this 1 acts there, you get square root n plus 1. And a dagger acting on n plus 1, it raises it, so you get n plus 2 square root n plus 2 x squared. You repeat this x3, you repeat it x4. And one thing that some people might try to do is to try to write this as a4 plus 4. My first year maths is bad, but let's say plus a3a plus a dagger 2a2. Basically apply the binomial, what do you call binomial theorem. So there might be, I think it's 1, 4, 6, 10. Just check, but there are some numbers here. Okay, let's just put wrong numbers. 1, 4, 6, 4, a 3, a let's say this is a dagger a3. I don't think this will work because these operators really do not commute. So you got 6 terms. For example, you got a dagger squared, a dagger, a dagger, a dagger. Let's say that you got 6 different terms which were like this. But if these were just pure numbers, then you got that you added them together because they were like terms. But here not. So you have to do this step by step. Right. And because of time, should I give the other hints, or I think maybe start with the lecture because this might take too long? Will everyone then be happy to do the problem, or is there a specific problem that you need a hint to? Okay, thanks. I remember those as like. Just notation. So yeah, some people call them ladder operators because what you start with is if you start with the nth state and you hit it with a dagger, this takes you to the n plus 1. But physically, right? So let me also maybe explain the terminology. So what people tend to use is that the picture that you have is that you have a ladder with your eigenstates, and if you start with n and you hit it with maybe a dagger, this produces that one, and similarly you end up in plus 1. Then if you hit with another a dagger, so people have this picture of a ladder, and these operators are called ladder operators. But I think Dirac, when he was introducing them in quantum theory in 1927, what he wanted to do was there's this problem that classically you have a system and it has this number, which is the number of particles, is actually fixed. But in your Hilbert space for quantum mechanics, the problem is that the numbers are not really fixed because of energy equals to mc squared. So if you have some energy in your system, you could create other particles that initially you didn't start with. So you might have started with maybe proton and an electron, and now you have other particles which are popping up from the vacuum. So you have to construct some Hilbert space where where these operators called create particles. So this n is labeling the total number of your system. And when A is on the system, then it creates another particle. So it might have created a PEP production, and you get this n plus 1 new vector, which is, so your final Hilbert vector space then will be made of n1 tensor product, n2 tensor product, and 3 dot dot dot, which, and this, so for the problem that we were dealing with, you saw that we were basically dealing with a state n1, n2, and n3. Just I labeled them nx and so forth. And maybe as an aside, the other thing, so I might have to go 30 minutes over time. Fine. I think, is everyone happy if I go over time? The full lecture will start in some time because people seem to be having difficulty. That says that for the things involving the harmonic oscillator, so not the harmonic oscillator, and the angular momentum operator. So the original problem that I gave you, from which I took from Zetili, it had this minus sign there. And the first thing was, what are the eigen, so I'm doing, this is not the same problem that you have. It's just there's this minus sign there which changes everything, and you will see why I changed it into a plus just now. So the first question that I was asking was, what are the eigenstates of this operator H0? For angular momentum, for everything to do with angular momentum, the eigenstates are usually L, M. They're labeled by the magnet, these two numbers. It might be that they are spherical harmonics or whatever, but basically they're sets that are labeled by L, M. And I think for the problem, okay, so I see that even for the problem that I gave you, but unfortunately Lx and Ly are not eigenoperators of these ones. That's why I changed that into a plus. But if it's a plus, right? Lz squared. So what I did, I just added, subtracted an Lz squared. And what is this then? So this operator then is, so these operators L squared and Lz squared, I know precisely how they add there. So the eigenstates are given by that, and the eigenfunctions, if you check, right, start there. Then when L squared adds there, you get L, I think 8 bar squared, L plus 1 minus, and then Lz, it's what I did in the previous lecture for the Zeeman effect. When Lz acts on this thing, gives you an H bar M. Then when it hits again, you get H bar M acting on L, M. So you get the same vector, but now it's being multiplied by some number, which that number is just H bar squared, L plus 1 minus M squared. Might be the other way around, but this is your so this is your eigenvalue, these are your eigenfunctions. And if I chose L to be 1, this is a triplet state because you have M can go from 0, can go from 1, and then there's the other state which is -1. We did this for the hyperfine type of splitting. Now, if you look at this state, then you plug the energy there, you get your energy. Take this one, plug there, take it, plug into that, because in essence, these your energy states, Lm. right? The energy that you will get is that this one only, let's me give an example. Say you find that your energy is 6, one is 4. You might find that this is 4, this is 6, this is 6. This is not degenerate, so you can apply first order and second order perturbation, but these ones here are degenerate. So then you have to label your vectors. One, maybe it's 1 and 0, 1 and 1. The other one might be 1 and -1. And then you form some matrix, then diagonalize that matrix. So let's say that in the end you find maybe that your thing, this is not the same problem. Let's say that the other one was 1. Okay, right. The once you try to diagonalize this matrix, you are going to get a set of eigenvalues. Maybe you get 6 plus or minus 6 lambda 2. The other lambda might be maybe 4, right? This means that your energy will be the energy of the original state. Right, say I've labeled this one maybe to be 1. This is just an example. So you get that it's going to be 4 plus you just add the eigenvalue corresponding to that vector, to the vector that you've labeled 1. So it might be that you add that 6 lambda there, and then E2 tilde will be the old energy plus maybe in this case it could be minus 6 lambda, and then E3, same energy, but now with this. These are your corrections. And then the good, let's say the wave function, right? Say now to get the wave function, it will be a linear combination. So you know that it's going to be, let's just for simplicity say that all these 3 states started with the same energy, which is wrong. But let's say you know that this is going to be 1, 0 plus 1, 1 plus 1, minus 1. Right? There will be some numbers here. You know that they have to be normalized, but you cannot use that the fact that this state is normalized to get these numbers. What you do, you find your you form this matrix W, which is due to these elements H, alpha, beta, which I calculated for the harmonic oscillator in the 5 minutes of the lecture. You diagonalize that matrix, and then you find your eigen function. So maybe there might be 1, 0, and -1. The numbers that are sitting here, you read them from your eigen vector. Say, let's call this is the eigenvector corresponding to first vector. So this vector, you just read them off. So it's 1 over square root 2. So you put 1 over square root 2, 0, which is the one corresponding to the second row, which corresponds to the second vector, what I call 2 hat. Similarly, 3, you read them as 1, so you get minus 1 over square root 2. So your new will just be 1 over square root 2, 1, 0, plus, or in this is 0, minus 1 over square root 2, this is square root 2, 1, minus 1. Okay. So this is how you get the eigenvectors. So I think now we should use those hints to be able to do the assignment. So let's go back to what we did the lecture. So we started 30 minutes late, so we might have to go extra. So someone asked if it's possible. Let me just check if they are here, because they couldn't somehow. Okay, they're not here, which is funny. But fine, let's just recap what we did with this variational principle on, I think it was Monday. So but I will be quick because yeah, some time. Just changed. So in general, the Schrodinger equation is a very complicated equation to solve. I'm going to use notation and use phi. Right. Now, in chapter 7, we relied very much on the fact that the Hamiltonian actually splitted. So we knew part of the Hamiltonian and we knew part of its eigen vectors. However, in general, we don't even know how to start. So what we then do, especially chemists, is that they guess some trial wave function and then they plug it into the Hamiltonian. It could be anything that they dreamt up of. The claim was that even though you cannot solve the exact Schrodinger equation and obtain the exact ground state energy, and you will see that we will do this for helium, even though you don't know the exact. If you just take any trial function and you plug it into the and find whatever value for the expectation of that trial that you get, it will always be an upper bound. And maybe you will see that maybe for most of our stuff, we take the Gaussian. So it will be depending on some alpha. So you end up with some family of trial wave functions, and it will always be an upper bound. And depending on the ones that will minimize, you can get closer by trying to minimize this one. So you might with EGS being smaller than the, and usually if you are clever enough to choose this psi-t correctly, you can actually saturate this bound. First thing that I would try to do on Monday was to prove this relation. So to do that, the proof splits into two parts. So the first part was first have to check that Cn squared was given by 1, then use this to check that this condition was this condition that you wanted to check was correct. So just to revise, say that your trial wave function, because these original wave functions were complete, you could expand them in terms of the orthonormalized wave function. So you get that I did this on Monday, so I'll be quick. Cn psi n Cm, another sum over m psi m. Right? There's linearity. This is a Hilbert space, so everything is linear. So you can take out the sum over m and n Cm, but you're taking stuff from the Dirac-Bra, so this is a complex conjugated because in general you aren't working in R but C. So similarly, when you take out the Cn, take out the Cm, then you're left with the overlap psi n, which I'm calling phi, but fine. Psi m doesn't matter because these things are orthonormalized. So the overlap between the n, what I did even for the harmonic oscillator, one, you saw the overlap between 1 and 0 or 0 and 1 was always 0 because the only time that they don't vanish is when it's 1 1. So similarly here, the only time that they do not vanish is when delta n m, and so this sum then gives you m n cn cm delta n m. Then you apply that. So this sum, the only time that it doesn't vanish is when they are equal, so you end up with the sum over m, or if you want over n, doesn't matter, of cn squared. And because these things were normalized, you've just proven that cn was 1, which is part of the part 1 of the proof. In the second part of the proof, let me erase everything. You then look at what happens once you try try to calculate this expectation value of the Hamiltonian using those trial wave functions. So this will give you psi h psi, right? And then you expand them because so this gives you cm psi m. Then you get h acting on sigma n cn psi n, right? And now you know what happens when h acts on psi n, right? M n cm star cn, right? And you are left with what's h acting on psi n. This just gives you en. Then you're left with overlap psi m psi n. Repeat the same thing. This is delta mn. So you ended up with mn cm cn star delta mn, but there is that en then. So this vanishes unless m equals to n. So you end up with sigma n e n c n squared. But by definition, you know that the ground state is the lowest. So any other energy, nth energy will always be greater than the ground state. So if you take sums, so this has to be greater than or equal to the sum over n of the ground state, because En is always greater than Eg, ground state, Cn squared. So you end up with that the expectation of your trial will always be greater than or equal to. EGS is a constant, so you take it out, EGS, and then you're left with sigma n Cn squared. This is 1. With part 1 of the proof was to check that these normalization constants were 1. So you get that H of your trial will always be bigger than EGS. And to check how this actually works, you look at the like by now you have seen that the most favored of all sorts of examples is the linear oscillator. It's just that in every chapter it would be getting more complicated, more complex, but it's like the harmonic oscillator is the one that we know how to solve, and it's a simple model. So whatever techniques that we have, we first check with this one, right? So let's say that for some reason you didn't know what you couldn't solve the Schrodinger equation, so you couldn't get what was En, and you couldn't also get what was psi n. But you're really interested in the ground state. So even for helium and H2 plus, the first thing that you can measure in a lab will be some number, and for helium maybe might be minus 79 electron volt. You don't know how you got that. Even for helium, the Schrodinger equation sometimes cannot even be solved, but you just want to see that number. So you use this principle. You guess something, and you know that the correct one will always be smaller than the expectation value of this thing that you guessed. So let's just say that because the easiest thing to integrate is always a Gaussian. So let's just assume that our trial wave function is given by the Gaussian. This thing has to be normalized. So the first thing that we did was psi. This has to be 1. This gives you minus infinity a squared e to the minus 2 alpha x squared dx. Just check that I do everything. What is this integral? Is Gaussian, so you just get the square root of pi over 2 alpha, if I'm correct. This has to be 1, so this gives you the normalization. Everything n has to in the end depend on this alpha parameter. Then you minimize the expectation of the Hamiltonian with respect to that alpha parameter. This will get you as close as possible to the ground state, and sometimes you get the so this means that this is 2 alpha over pi to the 1 over 4, right? Then you take this trial and then you find what is the expectation of h using this trial. So this gives you the x, a squared will come out. Remember that the expectation value of any operator is just psi h psi dx. So you end up with e to the minus alpha x squared minus h bar squared over 2m d2 over dx squared plus, because of space, I'm going to ignore the sub m squared omega. It's just an x squared term multiplied by e to the minus alpha x squared, right? So this gives you a squared, this, right? So integral dx. So when the derivative of x the first time, it's going to give you minus alpha x 2 e to the minus alpha x squared. This is the first derivative. Then when you hit it again, you get something like minus h bar squared over 2m. The derivative can add there, so it gives you minus 2 alpha. I might as well write everything plus, and then it hits again there, so you get minus alpha squared 2 squared squared. And again you get the half m omega squared x squared e to the minus 2 alpha x squared, right? And all these integrals you can do 2 alpha over pi to the 1 over 4 yeah, can't do them by hand, but that's what we did on the share. Lecture 4. Right. So that's what we did. Well, that's actually where we ended up on Monday. So these are the slides. Right. So as I did, you have the first thing you normalized, which is to try and find what that constant normalization constant was. So if you want, you can make use of that. But I just think for normalization, just use the standard Gaussian integral minus infinity e to minus alpha x squared. Is it true? This gives you square root of pi over alpha, which is what, right? Pi in this case is right. Find the normalization. Then you plug this into the expectation value for the Hamiltonian. This is the last part that I did on the whiteboard, right? And as I said, you get two contribution. There's this term there, but the derivatives twice. So you get it was acting on 2 alpha x e to the minus alpha x squared. So once it hits on the exponential, you get another term which is proportional to x squared, right? Which is basically this term. And then once the derivative x there, you only get an alpha term, which is this one, right? So which once you do all these integrals, which are easy to do, you end up with a family of energy eigenvalues, but you know that they all of them, right? So if you were to plot this, like all of them are upper bounds for your ground state. If you're looking for to get as close as you want to this, you first have to try and minimize this family of eigenenergies depending on alpha. And to do that, which is the next step, you differentiate with respect to your parameter. So if you differentiate, this just gives you that there. This gives you an alpha squared. Then you solve for alpha, so you get that alpha 0 will give you m omega over 2h bar. Then you take this value for alpha, or alpha 0, you plug it back into the E0. Right? And the value that you get for E0, in this case, you just get to be E0 over h bar over 2. And the value for this is normalization. This is alpha 0 somewhere, right? It's alpha 0. Alpha 0 you just solved. But this is the exact energies. So even though we didn't solve the Schrodinger equation in its full generality, the fact that what did was that we just guessed some wave function to be Gaussian. I think in the next example, I might give you some different wave function to try for the simple harmonic. You just guessed that, and then you ended up with some function h of alpha, and you minimize this, and then you found that EGS at best has to be this alpha 0, which is basically alpha 0. And once you solve that, you found that it actually saturates. So the trick is to find the best trial wave function, and if you choose it very cleverly, you might actually reproduce the exact ground state. But the next thing that I want to show is, given that we know the exact ground state, without solving the Schrodinger equation, can we then start to find the first excited state? So for the first excited state, again, you have to guess what the trial wave function for the first excited state will be. I think for most problems, if you find the ground state, you leave it there, but I'm just trying to show you how you will go about that. So it could be anything, but you know that these wave functions have to be normalized. So for the harmonic oscillator, you know that psi 0 and psi 1 and psi 0, which I wrote previously because I know they're labeled by integers. So I write this 0, 0. This is the harmonic oscillator. Yes. So they are orthonormal. So this gives you 0. So whatever trial wave function that you have to choose, it has to be orthogonal to 0. So this is already odd. Right? This is not odd. This psi 0 is already, if you check there, it's even. So this means that psi 1 at best has to be odd. So you try this one. Now, if you see here, you still have two parameters, b and alpha. B is normalization, so you can try to find what is psi trial of 1, psi trial of 1. So this gives you b squared x e to the minus alpha x squared. I didn't think by now everyone needs a b house. Let me just think. Why am I not? Yeah, this would have been wrong because this cannot be x. It has to be x squared. You are squaring the wave function. So again, this has to be 2. And this is not 0, but you can work it out. I think it's that integral that I just gave you. It's 1 times 3 times 5 times ... until you get to 2n minus 1 over. It's there in the previous slide. But once you do that, you can find what is the value for b. Right. In there. And everyone can do that. Don't have to bother with algebra. And This you don't have to do because you did this by construction. That's why you put that x there so that it becomes odd. Once it multiplies something which is even, you end up with automatically 0. And so we have already found what is b. What then we do is that we just take it and use that trial wave function psi t1 to compute the expectation value of the Hamiltonian. So this is psi1, psi1. You do same thing I did. There's going to be a term there, then this derivative, right? It's going to act. Yeah, just find what is d2 over dx squared. Try doing it in the previous, so you get x, e minus alpha x squared. I think everyone can do that, but in the end, you again end up with some family of eigen energies depending on this parameter alpha. Then you try to minimize them with respect to this alpha. So you get that E alpha 0, you get that by d over d alpha. This gives you, that goes away, alpha squared. You solve, yeah, which I didn't write down. But once you have solved for, basically, you can do this, right? So you get that alpha 0 will be, I think that the 3's cancel, might be m squared omega squared over 8 bar squared, maybe with a square root. Then you take this value for alpha 0 and then you plug it into this expression. This is, you get 3h over 2. Similarly, once you plug it, so there's an x there, the b we found, and you can check that these are actually the correct, and you can similarly do it for the next one, right? So you try this trial wave function. First thing that you have to do is try to find this normalization. So the normalization comes from psi 2, psi 2. This is 1, so you end up with c squared integral beta x squared minus 1. Like, I won't do the algebra because, as you will see, it gets messy. So you get things like beta x4, e to the minus alpha x squared, integrals. You do the integrals, you end up with something like that. So you know what is c, but you still don't know what is this beta and what is that alpha. But but you know that psi 2 and psi 1 has to be equal to 0. So if you try to do that, you get dx c beta x squared minus 1 e minus 2 alpha x squared with an x. Let me see, why not an x? Let's see psi 0. Psi 0 was didn't have any x dependence. So do this integral, see what you know. I think this will determine maybe the alpha. Okay, determines the relationship between beta and alpha, right? This is what I was saying in the previous slide, that by Gram-Schmidt orthonormalization, if you remember, even last year, the Hermite polynomials are orthonormal or orthogonal. So 0 and 2 will have to give 0. Try to work out what that will be. You will get this expression. So this determines what is beta in terms of alpha. And then do the step that I did. You just compute what is E2. So E2 will be dx psi operator on 2, differentiate twice that operator. It's going to be very long. Do the result integrals. Right. And then you find the expression, but now it's going to be depending on alpha and beta. You can try to do d over dE, and this is what most chemists actually do. So they end up writing some tail function that will be depending on lots of parameters. Then they try to minimize each one each one, and then once they find what is alpha 0 ice, this tends to give them a very good estimation of the ground state. So, but you already know that beta was given by some number multiplied by alpha plus some constant. So another way to do this is that you can take that value that we got once we were trying to find that 2 and 1 was 0, plug it here, so this eliminates these betas, and you end up with only an expression depending on the alpha. So yeah, there you can see that you only have this alpha here. Then differentiate this with respect to alpha. Essentially try to minimize this. Solve for that alpha 0, plug it back into this expression, and then you will find that this is what you get, even for C. Right? And again, this shows that this variational method actually works, because for the harmonic oscillator, we already knew the exact energies and also the exact thing. So to do it also, I think Griffiths also does it for the Dirac delta potential. You can solve it. It's easy to see how this comes about. Like the Dirac delta is 0 everywhere, so you're basically solving minus h bar squared over 2m d2 over dx squared psi given by e psi. So this, the psi, I just e I k x, and where just check, and then your energies then will be given by k squared, which is this one. Right, so this is similar to problem 2, because in problem 2, this is just an aside, in problem 2 I gave you something like this, d2 over d phi squared. It's the same thing here, so you know that your eigenfunctions are going to be e ikx, ik theta, or ik phi, depending on what I called them. But you also, phi is an angle, so you know that phi of 2 phi, so give you phi of theta. So this fixes this to be an integer, which is just m. But for this one, I think it's done in chapter 2. You can check that this is the exact ground state energy, but now you want to use the variational principle to see if you can actually get closer to that exact number. So you try some wave function. Again, the type one, the most popular one is usually the Gaussian, but it's either the Gaussian or I forgot what this one is called, or this one, because you want something that will actually vanish at infinity. If you can't just take this to be x squared, because x squared doesn't vanish at infinity, and the reason for that is you want normalization. So if you had chosen it to be x squared, it's not going to vanish at infinity. So again, they chose that one. I think a will be the same constant that we got previously. Let me just think. So the only thing that you have to get, and also this part, right? We haven't really changed anything. It's minus h bar squared over 2m d2 over dx squared, acting on side psi. It's the same trial wave function, so the physics doesn't change. You get the same expressions. So the only thing that you have to get was what is the expectation value. And actually, I think this might be very helpful for the exercise. So that if you're choosing the one-dimensional trial wave function to be the Gaussian, this part here will not change. So the only thing that you have to get was what was v minus alpha a squared, right? Expectation it's psi v psi. Already taken out these other constants, so this is just a delta function, and you're left with e to the minus bx to the minus bx. So Dirac delta function, you know how to integrate, only contributes at 0, so this gives you minus alpha, and once you solve, you just get square root b once you've done the algebra. So you get some energy, some family of energies that are depending on some parameter b, and from the theorem that will prove that the ground state will always be smaller than this E of B. But to get closer and closer to the correct one, you have to minimize this. So you take dE as a function of B with respect to dB. So it's equals to 0 to minimize that. So you just get h bar squared over 2m minus alpha. This gives you 2 pi. The B will be at the bottom, 2 pi 1. This you solve for the b, for the parameter. Once you have the parameter, just plug it back into the expectation value, and this, in this case, you don't get the exact thing because the wave function, I don't think is Gaussian, but you get something which is 1 over pi 0.31 minus, and this is greater than that, so even that is correct. And sometimes you might have to choose trial wave functions that are piecewise. That are piecewise, but for this one, so here you might have chosen something between 0 and A to be that, the other one to be that, and to be 0 everywhere. Right? So the first thing again is to find what that normalization factor would be. Right? Remember that you don't really know what the wave function is, just guess the wave function is depending on some parameter. You first have to find two sets of parameters. The normalization one, you get just saying that psi and psi have to be 1. So this fits into 0 to a over of a squared, square the wave function. So this gives you a squared plus a squared integral of a minus x squared from a over, this is easy, we've done this before. Check what you get for a. This is your a. However, in the Dirac equation, you also have to find what is d2 over dx squared, and I think if you differentiate that, you get, this is a there and this minus a there, which is a step function, and you have to use the fact that derivative of the step function by the Dirac delta function. Right. Once you d2, so plug that into there, then again do the algebra. So that one contributes is psi 0, this one only contributes this one psi a, this one not sure wasn't a over 2 or whatever. Once you compute everything, you get it's 12, and I think 12 pi 3 point something, so this is like 9, so the thing that you get, it's indeed bigger. So I think, let's see what's next. So the next thing that we will discuss then will be the helium, the ground state of helium. So we know that the ground state of helium, we measure it experimentally, is given by this value. We want to actually calculate it. Unfortunately, the problem exactly, especially because of this term. This term is the interaction between the electrons will be what will make life difficult, but we can have a break. Then in the next lecture, that's what we will be doing. I suggest a 20-minute break, so we will start at 10. Stop recording.